And hello everybody, this is Nat. This is another MET video. Today we're now going to go through question 2 of 2010. So first we need to find out and prove something which involves the fact that root 2 and root 3 are irrational. So you're going to square both sides on the equation. So what do? We put square brackets over them? No, what do? We do this. There, and then we're now going to square both sides. 2a squared plus 2 root 2ab equals to 3c squared. Wait, I forgot a b squared term. Here we go. And then we're now going to solve for the only irrational number here, root 2. So that means we're going to move all the terms except the root 2 term to the other side, which will give you 3c squared minus 2a squared minus b squared. And therefore, root 2 equals to 3c squared minus 2a squared minus b squared over 2ab. But we just say here that root 2, root 3, and root 2 over 3 are all irrational numbers. So that means this is a nonsense statement. Let's write down this here. Font size is a problem right now. Something serious. Much better. So therefore we can proudly say that root 2 is an irrational number. Yay. And now suppose now we're moving into Euclidean 2 space where flatland is held. Suppose now that mn are integers such that the distance from the point mn to root 2 root 3 equals to the distance from mn to root 2 root 3, so that m equals to big M and n equals to big N. What are we going to do? We're going to use the Euclidean distance formula. What's the Euclidean distance formula? Blech, might sound scary, but it's just another way of finding the distance between 2 points using a formula, x1 minus x2 squared plus y1 minus y2 squared. This is basically telling us that we can remove the square roots right now because we're now doing inequality, and who cares about square roots right now? So we can write, sorry, my pen. Okay, let's write m minus root 2 squared plus n minus root 3 squared equals to big M minus root 2 squared plus big N minus root 3 squared. Got that. And then we're going to expand the brackets, which will give us m squared minus 2 root 2m plus 2 plus n squared minus 2 root 3n plus 3 equals to big M squared minus 2 root 2 big M plus 2 plus big N squared minus 2 root 3 big N plus 3. There you have it. And we are now going to take off some terms. We can take out the constant terms because they are on both sides of the equation. The trick now is that we're going to rearrange this equation into the form a squared plus, no, it's a root 2 plus b equals to c root 3. This is basically telling us that we try any linear combination of a and b of root 2 and 1 to get root 3. As you can see, if the linear combinations evolve to some form of q, which is the rational numbers, let me draw a big Q here. This is how I usually write q. Then it's impossible, we can't do it. So what we're going to do is that we're going to arrange this equation into this form, which will therefore give us 2m plus 2m minus 2m root 2 plus m squared plus n squared minus big M squared minus big N squared equals to 2n minus 2 big N root 3. So this is impossible. Therefore, small m equals to big M and small n equals to big N. What's this telling us? Basically, there are no grid points equidistant from root 2, root 3. If root 2 and root 3 are in Q, which again is the field of rational numbers, then m may not be equal to m, and n may not be equal to n. But unfortunately, this has been first proved by Pythagoras and his friends that root 2 and root 3 are irrational numbers. So therefore, small m equals to big M and small n equals to big N. However, we can find rational approximations of root 2 and root 3. Some of the rational approximations to root 2 include 17 over 12 and 577 over 408. Enough beating around the bush. Let's go to the next part. Given real numbers a, b and a positive integer pair, let n equals a, b, r be number of integer pairs x, y such that distance between points x, y and a, b is less than or equal to r. So explain why this is a multiple of 4 for any value of r. So what do? We are now going to draw a square. So pretend that, let me draw 4 text boxes here. This is our origin. This is 0, 1. This is 1, 0. And this is 1, 1. What are we going to do now? We're going to draw a point in here. Yes, a point. Sorry, this point is a bit big. And this point is going to be exactly half-half. Let's write this down. And you see why? It's in the middle of 4 grid points. Therefore, n 0.5, 0.5 r is a multiple of 4 because 0.5 is in the middle of 4 integer grid points. Hence n, let's use the notation, 0.5 r is a multiple of 4 for any r. Now, if we pull over to decimals, hold on, it will take a while to go on to decimals. So here we are in decimals. So what we're going to do is that we're going to draw a circle with radius 0.5. Obviously, this is not going to be a very good drawing because I'm not very good at drawing in decimals. Yeah, quickly. And our radius is r. So this should mean that our r, we're going to slide it around here. Let's count the grid points. So first we are r equals to 0. Then look 0 on them. Then at around 0.7, which is root 2 over 2, it becomes 4. Then when it goes to I can't remember which one it is, it goes up to 12. Then 16. Then, I'm not sure now, 24. Yeah, 24. So therefore, it's always a multiple of 4 for any r. Now, here's the catch. Explain why n root 2 root 3 r equals to k when there's a positive number r. Wanna know why? Prepare yourself for this. Since, let's write down, since square root of 2 square root of 3 is irrational, because it's an ordered pair of 2 whole numbers and they're both irrational, that means they're irrational. Since square root of 2 square root of 3 is irrational, there are no 2 grid points that are equidistant from this point. Hence, let's not write the hence. So we wrote down our reason. This is basically telling us that since there are no 2 grid points that are equidistant from this point, that means the graph, when k increases, will not gobble up 2 points at a time. So in a sense, this circle's feeling hungry. It just wants to gobble up 1 point at a time. While this half-half circle is so greedy, it wants to take 4 at a time. Haha, hope you like the greedy analogy. Oh, and besides, we're gonna plop into decimals again and see how this has an effect on our circle. So we're going to write square root of 2 here, square root of 3. Then we're going to write, okay, there's 1, there's 2, there's 3, there's 4, there's 5, there's 6, there's 7, there's 8, there's 9, there's 10, there's 11, there's 12, and then you keep going along, then you see the circle gobbling up 1 point at a time. And you just want me to illustrate the grid points, there will be a Desmos graph link in the description. So, see you in another MAT video.